Okay, so now that we have defined the concept of orthogonality and orthogonal basis, how can we decompose any item of our vector space in an orthogonal basis? And that's going to be a very nice result, actually. Well, probably maybe one you foresaw because you already know how to work in R2 or 3 and so on. But let's see. Okay, let's see this what this result is telling us. All right, for all x in E, x will be written as, well, sum of coordinates in the basis times the basis vectors. Okay, something like this. And in other words, what it means is that the coordinates of x are going to be given by the inner product of x with the vectors of the basis. All right, so let's see that. Let's see how that works. Actually, what I want to prove, okay, so x belongs to E, he has dimension n. It means that x can be written as x1, x2, xn in basis. That would be the coordinates of x in the orthonormal basis, E1, E2, En. Okay, orthonormal. So, what I want to prove is that the xi are actually given by scalar product of x with ei, the corresponding vector. Okay, so let's prove this. Actually, it's so let's start from that. What is really x ei? All right. So if x has coordinates x1, xn in that basis, it means really that x is written as x1 e1 plus x2 e2 plus xn en. Okay, that's what it means to have that our element x has those coordinates. Right, so x, in other words, I can write this with a nice sum. That's the sum from I is equal to 1 to n of xi ei. All right, so I'm going to use this definition of x and work it in that scalar product, in that inner product. So what does this give us? Let's take some space here. If I want to compute x with ei, that's going to be, so I'm just substituting x by the sum that I wrote earlier, so 1. So let's maybe take another index so that I don't mistake the I on both sides. So the sum from k is equal to 1 to n of xk ek, scalar product, inner product with ei. Okay, I'm going to use the linearity property of the scalar product. Remember that those xk are real numbers. They are the coordinates of x in the basis. So using the linearity of this inner product, I get that this is really the sum from xk, k is equal to 1 to n, of ek, scalar product ei. Okay, and what you remember that this is going to be, well, that as the ei make an orthonormal basis, it means that ek, ei, first of all, they're orthogonal, so equal to 0 if, well, ek, if k, sorry, k is different from I, and it's equal to 1 if k is equal to I. Okay, so in that sum here, the only non-zero term is going to be the one corresponding to the I, right? Because all the other ones, they correspond to 0 factors. So we get that x ei is going to be, well, it's checking, it's taking only the ith elements. So xi times ei ei, And so we already know that this is 1 because the norm of the vectors are 1 because it's an orthonormal basis. Okay, and then for the next proposition, actually, we can just work from here. Okay, let me erase some of the stuff so that I've got a bit of room to write. So the next proposition tells you that now, okay, we still have this orthonormal basis, sorry, and we take two elements, x and y. They have the corresponding coordinates that we have already calculated in that basis. And so what is going to be then the inner product of x with y? Okay, so we just have to write what it means. I'm taking, well, maybe you can pause here and try to do the calculations by yourselves. What I am going to write is that x is that linear combination of xiei, y is the linear combination of yiei, and so what are we going to get? Okay, so pause here and do the calculations by yourself. Okay, so if you do the details, that's going to be sum of xiei with sum of y. I should take a different, maybe I'm going to take a j here, and I'm going to take a k here, yk, ek, okay. So j equals 1 to n, k equals 1 to n, and I'm using again linearity on both sides, so it's going to be, so linearity for the first one, j equals 1 to n of xj, so I get ej sum of yk ek, k equals 1 to n. And then I'm going to use linearity on the second argument, so I still have my outer sum xj. Here I get, so sum for k equals 1 to n yk ej ek. Okay, so here I've used linearity on the second argument, and again, that's the same idea as before. This is going to be 0 if j is different from k, or more precisely, if k is different from j, and 1 if k is equal to j. So that is selecting only the jth component. That's going to be yj, ej, ej. Okay, so I get that's the sum j is equal to 1 to n of xj, yj. Oh, because, well, that now is 1. So that's really the sum of xj, yj. 1j, 1 to n. Okay, and if you plug that with the same x, you get, what you get? You get the square, right? The square of, so the norm square is the sum of the squares of the components, which you already sort of knew. Okay, good.